Okay, so let's unpack this. You're planning a road trip, a serious one.
Right.
Maybe uh, crossing the Rockies or driving from Paris to Berlin. You get in your EV and you drive for 1,000 kilometers,
Which is what, over 600 miles?
over 600 miles on one single charge. No range anxiety, no staring at the percentage meter. And when you finally do stop, it's not for an hour. You plug in, grab a coffee, 10 minutes later, boom, you're back at 80%.
It sounds like the holy grail of electric vehicles, doesn't it? I mean, that's the stat we've been promised in press releases for, like, the last decade.
Exactly. It always came with a prototype that, never quite made it.
Never saw the light of day.
For years, that kind of performance was basically vaporware, always 5 years away.
Mm-hmm.
But here's where it gets really interesting. Today is Tuesday, February 10th, 2026, and the landscape. It seems to have shifted right under our feet.
It certainly has. We are not looking at theoretical physics anymore. We are looking at a supply chain being poured in concrete as we speak.
So today we are diving into a massive strategic pivot. Or maybe vindication is the better word. We're looking at Toyota,
Mm-hmm.
the company that, let's be honest, took a real beating in the media for dragging its feet on EVs. And now they're poised to potentially lead the next generation of battery tech. And the wildest part, they're doing it with a massive Japanese oil company.
It is such a fascinating twist. We're going to look at how Toyota and Idemitsu Kosan are turning literal oil refinery waste into the future of clean energy.
It just sounds so counterintuitive, oil saving the electric car. But before we get to the chemistry, which I know you're excited about, let's talk about the elephant in the room. Or maybe the tortoise.
You're referring to the Toyota is anti-EV narrative. That really dominated the headlines for the first half of this decade.
I am. I mean, rewind to 2023 or 2024. Tesla was the market darling. BYD was just exploding out of China. And you had Akio Toyoda, the CEO at the time, basically saying, hold on, we need a multi-path approach.
Right, hybrids, hydrogen, and EVs.
He didn't want to go all in on just batteries immediately,
Mm-hmm.
and he got hammered for it.
Oh, he did. The criticism was intense. The perception was that Toyota was just technologically lagging, stubbornly clinging to the combustion engine. But if you actually look at his argument, it was never about hating EVs.
What was it about then?
It was about resource allocation and carbon reduction per dollar spent. He argued that rushing into a full switch before the grid and the tech were ready, it just wasn't the most efficient path.
And now that we're sitting here in 2026, looking at the scoreboard from last year,
Mm-hmm.
how did that stubbornness work out for them?
Well, looking at the 2025 numbers, it is really hard to argue with the results. Toyota had an absolute record, 11.3 million cars sold globally.
That's their highest number ever.
Ever. And while the pure EV makers were struggling with demand plateaus and price wars in 24 and 25, Toyota's hybrids just kept flying off the lots.
So essentially, while everyone else was burning cash, fighting over the early adopter EV market, Toyota was just stacking cash from hybrids.
Precisely. And here is the strategic brilliance that I think people missed. By not rushing headfirst into those early, and you could argue inefficient, generations of EV battery tech.
The really heavy liquid lithium-ion packs from the early 2020s.
Exactly. They bought themselves time. And they used the massive profits from those 11.3 million hybrid sales to fund the R&D for the next big thing.
So the tortoise didn't just win the race.
Yeah.
The tortoise used the prize money to buy a jetpack.
In a manner of speaking, yes. And that jetpack is what we're discussing today. Solid-state batteries. But they couldn't do it alone, which brings us to that unlikely marriage you mentioned.
Right, Idemitsu Kosan. This is a legacy big oil company, petroleum refining, the old guard. Why on earth is the world's biggest car maker partnering with an oil refiner to make the cleanest batteries in history? Is this just greenwashing?
It's definitely not greenwashing. It's hard chemistry. When you refine oil, you get byproducts.
Stuff you don't want.
Right. And one of the major ones is sulfur.
Sulfur, the smelly yellow stuff.
The very same. Usually, sulfur is considered low-value waste. It's a headache.
Right.
But Idemitsu has been researching this since 2001, so for 25 years now, and they discovered that you can turn this waste sulfur into something called sulfide solid electrolytes.
Okay, let's slow down and break this down. We hear solid state all the time. But why is a sulfide solid electrolyte the specific secret ingredient here? Why not use like ceramics or polymers?
So to understand that, we have to look at why solid-state batteries have been so notoriously hard to build. The problem is mechanical durability. Imagine the battery. When you charge and discharge it, the materials inside actually expand and contract.
Like breathing.
Exactly like breathing. The cathode and anode, they swell and they shrink. In a liquid battery, that's fine. The liquid just flows around it. But in a solid battery, if you have a rigid material like a ceramic, what happens when the insides expand?
It would crack. Like ice cracking when it freezes.
Precisely. The contact points break. Once those cracks form, the ions can't flow, and the battery is, well, it's dead. It loses its capacity almost immediately. This has been the failure point for decades.
So the battery literally breaks itself apart from the inside just by being used.
Yes. But this is where Idemitsu's sulfur research changes the game. Sulfide electrolytes are unique because they have high ionic conductivity, meaning power moves fast, but mechanically they're what we call ductile or malleable.
Malleable, so not brittle like glass.
Think of it more like a dense clay or maybe a hard rubber, because they have that plasticity. When the battery materials expand and contract, the sulfide electrolyte just flexes with them.
It maintains contact.
It maintains that physical contact. It doesn't shatter. It adapts.
That is just fascinating. So they're taking a waste product from the dirty energy of the past oil refining and using its specific physical properties, its squishiness, if you will,
Right.
to solve the biggest mechanical headache of the clean energy future.
Correct. And this also solves the scalability issue. Because the material is malleable, you can process it using standard manufacturing techniques. You can press it at room temperature. You don't need those high-temperature ovens like you do with ceramics.
But wait, if it's so perfect, why hasn't this happened sooner? There has to be a catch.
The catch is moisture. Sulfide electrolytes are incredibly sensitive to water. If they touch moisture in the air, they degrade and release hydrogen sulfide gas, which is toxic. So the manufacturing challenge isn't the material itself, it's building them in these ultra-dry rooms.
That sounds expensive.
It is capital intensive. But that's the news for February 2026. Idemitsu isn't just experimenting anymore. They are building a massive pilot plant right now to mass produce this stuff. They're scaling up from grams in a lab beaker to hundreds of tons.
And the timeline on that, because I feel like I've heard 2 years away for the last 10 years.
The plant is scheduled to finish late next year, 2027. So this moves the tech from, science project to factory line. They're targeting a commercial launch for 2027, 2028.
So we are talking about real cars on the road relatively soon. But I want to circle back. We've established the solid part helps with the cracking. But what does this actually mean for performance? Why is it better than the lithium-ion battery in, say, a 2024 Tesla?
It comes down to energy density and safety. In your current EV, that liquid electrolyte is a bottleneck. It's flammable, so you need heavy cooling systems, safety shielding,
Right.
and ions move through liquids somewhat slowly, which generates heat during fast charging.
Right, which is why my charging speed just drops off a cliff after 80%.
Exactly. Solid electrolytes let ions move much faster. That's how we get that 10-minute charge. But more importantly, solid electrolytes are thermally stable. They handle high voltage and heat so much better.
So you don't need as much cooling gear.
Correct. You can strip out the cooling loops, the heavy casing, and you can pack the active materials much tighter. The result is a battery that is physically smaller but holds significantly more energy.
And that's how they get to that 1,000-kilometer range target.
That's how they hit the target. And they're already targeting 1,200 kilometers for the second generation.
That is a game changer. That's effectively killing range anxiety forever. But let me play devil's advocate. 2027 or 2028 is still a couple of years away. For the listener whose lease expires this year in 2026, is Toyota just telling them to wait?
Not at all. And this is where that multi-path strategy really shows its strength. While solid state is the headline grabber, the mainstream rollout is happening literally right now in 2026.
Okay, so what are the options if I walk into a dealership later this year?
Well, they've categorized their new battery roadmap into 3 tiers, which is smart. You have your popularization tier, your performance tier, and then the high-performance solid-state tier.
Let's talk about that popularization one. Because let's be real, most people are not buying $100,000 supercars. They want a reliable daily driver.
Exactly. And this is the bipolar LFP battery. This is a piece of engineering that I think just doesn't get enough press.
Okay, bipolar. I assume we are not talking about mood swings here. What does that mean for a battery?
No mood swings. It refers to the internal structure. In a traditional battery, imagine a stack of pancakes. Each pancake, each cell, is wrapped in its own casing with its own connectors wired to the next one. There's a lot of dead space.
Lots of copper, lots of plastic, wasted volume.
Right. Bipolar technology changes that. Instead of wiring them externally, the cells share a current collector. The cathode of one cell is backed directly against the anode of the next one on the same plate.
It's like a roll of coins.
Exactly like a roll of coins. The electricity flows straight through the stack. This eliminates all the terminals and connectors between the cells.
I see. So you're just removing parts.
You're removing a lot of parts. This reduces internal resistance, so it's more efficient, but crucially, it reduces the volume and the cost. Toyota estimates this structure, combined with cheap LFP chemistry, makes the battery 40% cheaper to produce than the current BZ4X battery.
40% cheaper. That is massive. That's the difference between a $50,000 car and a $30,000 car.
Exactly. That's how you get mass adoption. It has about 20% more range than the current generation, but the price drop is the real revolution here.
Okay, so the roadmap is buy the cheap bipolar LFP car now if you're on a budget. Buy the performance liquid battery if you want premium. And wait for solid state if you want the holy grail.
That's the gist of it. It's becoming a nuanced market with real options rather than a one-size-fits-all approach.
It makes sense, but there's another factor here that isn't chemistry or cost.
Yeah.
It's physics. And honestly, it's about style. We've all noticed that EVs tend to look a certain way.
Bulky.
Yeah, tall, blocky, crossovers, miss sleek cars.
Well, that bulk is dictated by the battery. The industry standard has been the skateboard design. You put the battery under the floor.
Right.
But that skateboard is thick. The battery pack in the current BZ4X is about 150 millimeters high. That pushes the floor up, which pushes the roof up. You end up with a tall car.
And a tall car means more wind resistance.
Exactly. Aerodynamic drag is, well, it's a huge factor. So even if your shape is slippery, if the car is a giant brick, you're fighting the air. This kills your range at highway speeds.
So how does the new tech fix this?
Toyota is obsessing over something they call the hip point. They are using the higher density of these new batteries, both the advanced liquid and the solid state, to physically shrink the height of the pack.
By how much?
They're targeting a reduction from 150 millimeters down to 120 for standard cars, and for sports models, they're aiming for 100 millimeters.
100 millimeters, that's 4 inches. That is incredibly thin for a battery pack.
It is, and that 50 millimeter difference changes everything for the designers. It allows for a low hip point. It means you can design a car that sits low to the ground, cuts through the air like a knife, and looks like a proper sports sedan.
So we get better range not just because the battery holds more energy, but because the car itself is more efficient.
It's a virtuous cycle. A smaller battery allows a lower car. A lower car has less drag. Less drag means you need less energy to move it.
It really feels like we are witnessing a convergence of industries here. I mean, we started this deep dive talking about a battery, but we've covered oil refining, chemical engineering, mass manufacturing, and aerodynamic physics.
That is the nature of this energy shift. It's not happening in a silo. You have an oil company realizing its future isn't burning oil, but using the waste from it. And you have a car company realizing the race wasn't a sprint to be first, but a marathon to be scalable.
And let's not forget the safety in numbers. We've talked about Idemitsu, but Toyota is also deeply integrated with Sumitomo Metal Mining for the cathodes. They're building a fortress of a supply chain.
They are. And that's the difference between a startup and a legacy giant. They aren't just hoping the parts show up. They are ensuring they control the ingredients from the mine to the refinery to the road.
So what does this mean for you, the listener? If you're driving that gas car and wondering when to jump, the answer is getting clearer. 2026 is bringing cheaper, longer-range options that actually make financial sense. And if you're the type who holds out for the best, 2027 or 28 might just bring that holy grail car.
The anxiety of range and charging time, it's about to become a historical footnote. We're moving from the early adopter phase to the industrial maturity phase.
I love that. Before we wrap up, though, this whole sulfur thing has me thinking.
What's on your mind?
Well, we spent a century digging carbon out of the ground. And now we're finding out that sulfur, this thing we thought was garbage, a nuisance, is actually the key to the ultimate green battery. It raises a huge question. What else are we throwing away?
That is the provocative thought for the day. If the byproduct of the fossil fuel era is the bridge to the renewable era, what other industrial leftovers are sitting in slag heaps or landfills right now? We might be sitting on the periodic table of the future, disguised as the trash of the past.
A fascinating thought to leave us with. It changes how you look at a landfill, doesn't it?
It certainly does.
Now, we know your time is valuable, and we really appreciate you choosing to spend these 15 minutes learning with us. We hope we've helped make this complex topic a little clearer for you.
Yes. Thank you for listening. It's always a pleasure to dive into these topics with you.
Until next time, keep exploring. This has been The Deep Dive. Thank you for listening.